This is the first lecture about gases. Gases are especially important to us because our entire atmosphere is made up of gases. Some of the properties that make gases unique you're already familiar with, and some of them you aren't, but I want to review them quickly for you. Gases are the only phase of matter that expands spontaneously to fill whatever container they're put into. Gases are highly compressible, and that is because the space between gas particles is so large that we can squeeze them together, in other words, compress them. All gases form homogeneous mixtures or solutions with all other gases. So liquids and solids can make homogeneous solutions or heterogeneous solutions. In the case of gases, they're always totally compatible. So here's a new concept which we will talk about later. It's called Avogadro's law. And that says that equal volumes of gases contain equal number of molecules. So imagine that you have one balloon that you fill with the air from your lungs and another balloon that you fill with helium. Those two balloons, although they contain different gases, assuming they're blown to the same volume, will have the exact number of gas molecules in them. That is not the case with liquids or solids. You could have a glass full of water and another glass full of, let's say, alcohol, and if you could count the molecules, there would be a very different number of molecules of water versus alcohol, mainly because of the density, the way the molecules are packed together in the two liquids. But for gases, again, because they're so far apart, equal volumes, equal number of molecules. All right, this is called the kinetic molecular theory. There are 4 parts to it, and this is just flat out memory that you will need to be familiar with. The kinetic molecular theory is the basis for all the subsequent gas laws that we're going to learn about, so it's important to know about. The first tenet of it says that gas particles are in constant random motion, and that the volume of the gas particles themselves is negligible compared to the huge volume between the particles. That's an important assumption, again, to simplify the gas laws that we use. Here's probably the most important one. Gas pressure is due to collisions of gas particles with the container walls. That's an important part of it. So gas pressure is not due to collisions of gas molecules with each other, okay, just with the container walls. And actually another pretty important one is Kelvin temperature is directly proportional to the kinetic energy of that gas. So there's a linear relationship between those two, and measuring the temperature of something is actually one of the most important pieces of information we can get is the kinetic energy of that system. All right, so reiterating that I said gas pressure is due to collisions of the gas molecules with the container wall. So if we talk about increasing pressure, anything that increases the frequency of collisions against the container wall will increase density. So there are 4 different things that can increase the frequency of collisions with the container. Let's look at what those are. Obviously, the number of gas particles. If you dump more gas particles in the same size container, you're going to have more frequent collisions with the container wall. The volume of the container will change the pressure. Okay, if you make it a smaller volume, you're going to get more collisions and more pressure. If you make it a larger volume container, you will get fewer collisions and therefore less gas pressure. And finally, if you change the speed of the gas particles, you will get more collisions and more pressure. And so obviously, how would we, the easiest way to increase this or change the speed is to change the temperature. All right, so a little bit of clarification on the most important gases to us. That is, what is atmospheric pressure? You know there are several gases that make up the atmosphere. Atmospheric pressure is literally the force or the weight of the air, molecules of air bearing down on us and everything else on the earth, actually. We can't feel that force because we've acclimated to it, but it is definitely there and it's quite strong. So as you go to higher altitudes, let's say you climb a mountain, the air pressure you experience is lower, and that's because on top of a mountain you have fewer gas molecules weighing down on you, less pressure. There are two simple instruments which measure gas pressure that I want you to be familiar with. One is the barometer, and that's what we use to measure the air pressure outside each day. And although atmospheric pressure hovers around 760 millimeters of mercury, by the way, millimeters of mercury is the same thing as torr, T-O-R-R, just so you're familiar with that. Oh, here it is. Okay, so it hovers around 760, but they're, depending on whether we have a high pressure front or low pressure front, that 760 can go up or down, and also depending on what altitude you're at. So a barometer measures the atmospheric pressure. It typically uses mercury in a container, and atmospheric pressure, as I told you, all of the molecules of the atmosphere are colliding with the surface of this mercury and exerting a pressure, and as a result of that pressure, mercury goes up a tube that it's immersed upside down in the mercury, and scientists literally measure the height that the mercury has climbed up the tube, and that's literally where the units millimeters of mercury came from. There's also another instrument called a manometer. Rather than measuring atmospheric pressure, it measures the pressure of some unknown gas that you're trying to get more information about. So make sure that you understand how a manometer works and how to do the simple calculation involved with it, because it will likely show up on your next exam. So let's see, we're trying to find the pressure of some unknown gas, and we hook it up to our manometer. In the middle, it's really just kind of a tube, but this tube has some mercury in it, just like the barometer did. And the other end of the tube is exposed openly to atmospheric pressure. So of course atmospheric pressure is exerting pressure down on the mercury, and your gas, as all gases, is also exerting a downward force on the mercury inside the tube. So whichever one of these gases, the unknown gas or atmospheric pressure, is exerting a stronger pressure, the mercury will be pushed down more. So let's look at this. Okay, so in this case, the mercury, it looks like the unknown gas or the high pressure gas has a higher pressure than atmospheric pressure because it's exerting a stronger force and the mercury is down lower than on the atmospheric pressure side. What do we do with that information? Well, on a manometer, you measure the difference between the height of the mercury from the unknown gas and the height of the mercury from atmospheric pressure. That difference is the difference in pressure between atmospheric pressure and the gas. So now, how do we find the pressure of this unknown gas using this H value? In this case, since the atmospheric pressure is lower, okay, in other words, the unknown gas pressure is higher, we're going to start with the atmospheric pressure, and we're just going to assume it's 760. Okay, if it's different, the problem would tell you. So 760 torr, or millimeters of mercury, plus whatever H is, and H was that difference, will give us the pressure of the unknown gas. Okay, so in this case, you want to, sometimes you're going to be subtracting, sometimes you're going to be adding, depending on whether the pressure of the gas is higher or lower. So let's go ahead and work another problem similar. All right, so take a minute and see if you can work this problem by yourself. What is the pressure of this neon gas? And this is a manometer. And see if you can kind of follow what I did on the last slide. So turn off the video, see if you can do it yourself, and then you can check your answer on the next slide. Make sure you pay attention to what has the higher pressure. Is it the atmosphere that has the higher pressure, or is it the neon gas? Well, hopefully you've tried this on your own, but you would notice, hopefully, that atmospheric pressure is higher than the pressure of the neon. So we're going to start with 748 millimeters of mercury, and we're going to subtract in this case because the gas we're trying to get to has a lower pressure. We're going to subtract whatever H is, and that's going to give us the pressure of the neon gas. Now the question is, what is H? I want you to be careful not to be fooled. Pay attention to units, as always in chemistry. Notice that the units of atmospheric pressure are in millimeters, and the units of H is centimeters. So the first thing you have to do is convert from centimeters to millimeters. You may already know that there are 10 millimeters in 1 centimeter. So 5 centimeters would be 50 millimeters. If you're a little shaky on that, which I would understand, often when you're doing metric conversions, you want to first go to the base units, which is meter. And I think most of you probably know there are 100 centimeters in 1 meter. So first you would probably put it in meters, which means 0.05 meters. And then go ahead and do a second conversion to millimeters. So 1 meter, there are 1,000 millimeters. And so that gives you the same answer, 50 millimeters. But be familiar with doing this conversion in particular. All right, so what do we have so far? We have 748 millimeters minus 50 millimeters. So that means the pressure of the neon gas is 698 millimeters of mercury. And here's it written out a little bit less sloppy, if you want to look over and make sure you understand it. All right, one of the last concepts I want to get across to you is once we start working problems, you will very frequently see something called STP. That is short for standard, whoopie daisy, and that's supposed to be temperature and pressure. And it's critical that you know what standard temperature and pressure mean. Standard pressure is atmospheric pressure, which could either be 1 atmosphere or 760 torr, or 760 millimeters of mercury. Torr and millimeters of mercury are the same. You do not have to work with pascals or kilopascals. And standard temperature for gases is actually 0 degrees Celsius. I'm not sure if it's sunk in before, but all gas calculations have to be done in Kelvin. So, and a lot of problems will give you Celsius. So one of the first things you need to do is convert from Celsius to Kelvin. So let me remind you what that is. Kelvin is degrees Celsius, and then you add 273. Kelvin will always be a larger value than Celsius. So if you get mixed up what to add the 273 to, just remember Kelvin comes later in the alphabet and it's always larger. Last slide for this first lecture. The gas laws are based on manipulating the 4 properties that define gases. One of them is temperature. Again, must always, always, always be in Kelvin. The other is pressure, of course, volume, and then number of moles. You might not be familiar with the symbol we use for number of moles, but it is a lowercase n. Again, a reminder, STP conditions, 0 degrees Celsius and 1 atmosphere. That's it for the introductory lecture about gases, and there are just several vocabulary and concept information you need to know from this lecture.